You might remember that the parabola has an interesting reflection property. If you imagine light beams leaving the focus of a parabola, something interesting happens. So it seems like maybe we should play the same game with an ellipse. Imagine light rays coming out of one of the two foci of an ellipse, and imagine that the ellipse itself is actually made of a reflective material so that the light beams coming out of the focus bounce off. Where do you think they would end up? Does anything nice happen? Well, print out the handout and sketch some light beams coming out of focus 1 here and see how they bounce off of the ellipse. Remember, the important property for reflection that we need to remember, that we sort of have to take physicists' word for, is that when a light beam reflects off of a surface, so here I've sketched the tangent line at this point where the light beam is striking the ellipse. When a wave like light bounces off of a surface, the angle that it makes coming into the surface is the same as the angle that it makes going out of the surface. So something like that. So pause the video and sketch several light beams coming out of the first focus and bouncing off of the ellipse and see where they end up. Okay, so hopefully you sketched several light beams. Just to finish this one that I started, it looks like maybe it's headed towards that second focus. That would be quite a coincidence if that were actually true. If I just happen to pick a single point where that works. So let's sketch a couple other light beams. So here's one. And to reflect it, it would need to, so it's coming in at that angle, so it's going to have to go out at the same angle. And yeah, that looks like it's going to the focus. And if we go over here, so this is coming in at that angle, so it's going to go out at that angle. And yeah, that's going to the focus too. It turns out that every ray emitted from one focus always bounces to the other focus after it reflects off of the ellipse. This has been taken advantage of in some peculiar architecture. If you make a large room in the shape of an ellipse, it's called a whispering gallery, because if someone stands at one point and whispers, and you stand at the other point and listen, you can hear what they say very clearly, even if they're very far away. And the reason is because when someone is standing at one focus and whispers, the sound waves all radiate out in all directions, but no matter what direction the sound wave is going, it bounces off of the walls and goes back to the other focus where you're listening to it. So all of the sound that is dispersing from the first focus gets reflected and focused back at the second focus. So I guess calling them foci is good terminology. Let's use this idea in an example. So let's design a whispering gallery that's 80 feet wide and that has 100 feet between the focal points. So our whispering gallery, we can make the major axis either way, so let's make it horizontal. And since it's a whispering gallery, it's going to have to be an ellipse. So let's set it up like this. Since we're choosing the coordinate system, we can put the center wherever we want. So we want this to be 80 feet wide, so that must mean this direction. Right? It can't be the left-right direction because then the major axis would be less than the focal radius, and that doesn't make any sense for an ellipse. So this vertical distance is 80 feet, and we want 100 feet between focal points. So let's put some focal points in here. So we aren't totally sure yet where the vertex of this ellipse is relative to the focal point, but we do know that the distance between these foci is 100 feet. And that means that the focal radius, that's from the center to one of the foci, must be 50 feet. Okay, so let's see what to do. Well, we know C is 50, and the height of this ellipse, the width, I guess, the vertical height, vertical width is since it's 80 all the way across, that means halfway across is 40 feet, and that's B. So now we have, right, once you know two of A, B, and C, you can always find the third one because in an ellipse, A, B, and C have a Pythagorean relationship. So B squared plus C squared equals A squared. And so now we can find A squared. So B squared is 40 squared is going to be 1600 plus C squared is 2500 equals A squared. So that's going to be 4100 is A squared. And so A is going to be the square root of 4100, which I guess is something like 10 times the square root of 41. So now we know that we knew the width of our ellipse to begin with, but now we also know the length. The length of this ellipse must be twice A. Remember, A is the semi-major axis, and so the major axis, the entire length of the ellipse, is 2 times A, and so that's going to be 20 times the square root of 41.